In the parallel circuit of figure 1 below, the RMS values of the three currents I1, I2 and IT are 18 amps, 15 amps and 30 amps correspondingly. Determine the values of resistance R and of the reactance XL. In every phasor problem, we choose one voltage or one current as the reference for angles, as the 0 degrees phasor. In this case, I'm going to choose this voltage as the 0 degrees phasor. That means that that voltage has 0 degrees. The current in this resistor, this one, I'm going to call that IR, has also 0 degrees because it has to be in phase with that voltage. The current in this resistor, which is I2, has also 0 degrees for the same reason. And the current in this reactor, which I will call IX, is at 90 degrees behind this one, so it has a phase of negative 90 degrees. So we can draw a phasor diagram readily. This would be the voltage phasor with its 0 degrees. This is the current I2, this one, in phase with the voltage, because this is a resistor, 15 amps with 0 degrees. We have to add to this current also the current IR, which is also in phase with the voltage. It also has 0 degrees. So this one is the current in IR. It's unknown so far, IR. And to those two currents we have to add a third current, IX, which is lagging 90 degrees behind the voltage. So that current in that reactor is this one. This is IX. And then we know that if we add together those two, IR plus IX, I gotta get 18 amps. Like so. And if I add together the three of those currents, I gotta get the total current, which is 30 amps. Like so. From this diagram, of course, we can compute what are the values IR in these resistors, this current, and the current in the reactor, IX. How? This angle here, theta, we find using cosine law, and then subtracting that from 180 degrees, we get the angle alpha. 18 times cosine of alpha is IR. 18 times sine of alpha will be IX. So that way we investigate what are the values of currents in R and in XL. We also know the voltage in those two elements, which is V, and V is no other than 15 amps times 460 volts. 0 degrees is the value of the voltage in each one of the three elements. If we find those currents, we use Ohm's law to find R and to find XL. Let's do that. This voltage, I repeat, is 4 ohms times 15 amps, that is 60 volts. 0 degrees, our convention. Now let's go to this triangle using cosine law. In this angle here, the value of theta is 130 degrees and some change. And the value of the angle alpha is 49.46 degrees. We are ready to compute IR and IX. These are the values of currents in the resistor, 11.70 amps, and in the reactor, 13.68 amps. If we divide the voltage 60 by each one of those currents, we obtain readily R and XL. R is 60 volts, 0 degrees, which is a real number, divided by the current 11.70, which is also a real number. It has a phase of 0 degrees, as we see that there. And that is the resistance we're looking for, 5.13 ohms, this resistance. Let's find the reactance XL. That reactance is just 60 volts divided by the magnitude of the current through that reactor, which we found is 13.68 amps, 4.39 ohms. If you're thinking, well, wait a minute, you're dividing real numbers to find the reactance, should you not, using Ohm's law, with complex number. Should this V voltage shouldn't be that a complex number V? Well, it is. It's 60 volts with 0 degrees, which is a real number. But you say, and the impedance of this one should be JXL. By all means, let's do it that way. We say, well, the impedance JXL would be the voltage 60, we know that it's a real number, divided by the current. By this current here, and that current has a value of 1368 amps with an angle of negative 90 degrees. Negative 90 degrees. When you perform the operation, what you get is J times the reactant that you obtain. You see what I did before was just dividing the absolute value of the voltage by the absolute value of the current, and that would have given me the absolute value of the impedance, which is no other than the reactance directly. And those are the results of this problem. Thank you very much.